Hi, and welcome to the first course in DataCamp's Data Visualization with ggplot2 series. My name is Rick Scavetta, and I'll be the instructor for this series. I've been training scientists on how to better understand and visualize their data since 2012. I'm very excited to bring my experience to DataCamp. So, what is Data Viz? Data visualization is an essential skill for data scientists. It combines statistics and design in meaningful and appropriate ways. On the one hand, Data Viz is a form of graphical data analysis, emphasizing accurate representation and interpretation of data. On the other hand, Data Viz relies on good design choices, not only to make our plots attractive, but to also aid both the understanding and communication of results. On top of that, there is an element of creativity, since at its heart, Data Viz is a form of visual communication. It's important to understand the distinction between exploratory and explanatory visualizations. Exploratory visualizations are easily generated, data-heavy, and intended for a small specialist audience. For example, yourself and your colleagues. Their primary purpose is graphical data analysis. Explanatory visualizations are labor-intensive, data-specific, and intended for a broader audience. For example, in publications or presentations. They are part of the communications process. As a data scientist, it's essential that you can quickly explore data, but you'll also be tasked with explaining your results to stakeholders. Good design begins with thinking about the audience, and sometimes that just means ourselves. This dataset contains the average brain and body weights of 62 land mammals. To understand the relationship here, the most obvious first step is to make a scatter plot, like this one. Two mammals, the African and Asian elephants, have both very large brain and body weights, leading to a positive skew on both axes. Here, applying a linear model is a poor choice since a few extreme values have a large influence. A log transformation of both variables allows for a better fit. So, although we begin with a rough exploratory plot, that informed us about our data and led us to a meaningful result. In the end, we'd probably want a cleaned up explanatory plot. Here's a classic example from Francis Anscombe, first published in 1973. When we imagine a linear model as presented in this anonymous plot, we imagine that we are describing data that looks something like this. But this same model could be describing a very different set of data, such as a parabolic relationship, which calls for a different model, or data in which an extreme value has a large effect, which becomes clear when the outlier is removed. And sometimes, the model may be describing a relationship where in fact there is none at all, because some extreme values may be incorrect. If we relied solely on the numeric output without plotting our data, we'd have missed distinct and interesting underlying trends. We can see that Data Viz is rooted in statistics and graphical data analysis. But it's also a creative process that involves some amount of trial and error. All right, enough examples. Let's get our fingers moving with some exercises. The first step in thinking creatively about data visualization is to appreciate that graphics are built upon an underlying grammar. To begin, let's consider one of the most well-known sentences in English. The quick brown fox jumps over the lazy dog. Every word in this sentence has a clear grammatical definition, and when we write text, we take great care to choose the grammatical elements so that we communicate a very specific message. If we changed any of the grammatical elements of this sentence, it would change the meaning, sometimes subtly, sometimes dramatically. The same concept holds true for data visualization. Graphics are built upon an underlying grammar. The Grammar of Graphics is a plotting framework developed by Leland Wilkinson and published in his 1999 book, The Grammar of Graphics. There are two key things to note about the Grammar of Graphics. First, graphics are made up of distinct layers of grammatical elements. And second, meaningful plots are built around appropriate aesthetic mappings. To continue our analogy to written grammar, the layers are like the adjectives and nouns, and the aesthetic mappings are like the grammatical rules for how to assemble that vocabulary. Let's explore grammatical elements first. There are three essential grammatical elements: data, aesthetics, and geometries. The data is obviously the data which we want to plot. The aesthetics layer refers to the scales onto which we will map our data, and the geom layer refers to the actual shape the data will take in the plot. The rest are optional layers. This includes the theme layer, which controls all of the non-data ink. In this course, we'll cover these first four layers, which will comprise your core competency. In the next course, we'll explore the remaining grammatical elements, the statistics, coordinates, and facets layers. This diagram gives an example of some of the terms we'll encounter in each element. Whenever we make a plot, we are choosing among these options and many others not displayed. By the end of the course, you'll be able to generate meaningful and publication quality exploratory plots using the first four layers. Once we've covered the remaining three layers in the second course, you'll be using DataVis as a tool for exploratory data analysis. Let's head over to the exercises and explore one of the datasets that you'll be using throughout the two courses. Now that we have some idea about the different grammatical elements of graphics, let's see how this works in practice. The grammar of graphics is implemented in R using the ggplot2 package. There are two key functions that ggplot2 serves. First, we construct plots by layering grammatical elements on top of each other. Second, we use aesthetic mappings to bridge the link between data and its visual interpretation. We are going to go through each grammatical element in depth in this and the next course. Here, I'll introduce a dataset which will be used throughout the videos, and we'll go over some simple examples. The bottom layer is the data element. Obviously, we need some data to plot. I'm going to use several different datasets in the course videos, one of which is the classic iris dataset collected by Edgar Anderson in the 1930s and thereafter popularized by Ronald Fisher. The dataset contains information on 3 iris species, Setosa, versicolor, and virginica. 4 measurements were taken from each plant, the petal length and width, and the sepal length and width. You're probably familiar with petals. They're the colorful part of a flower. Sepals are the outer leaves of the flower. They are typically green, but in this case, they're also colorful. There are 50 specimens in each species. The data is stored in an object called iris. There are 5 variables, the species and 1 for each of the properties which were measured. The next layer we'll add is the aesthetics element, which tells us which scales we should map our data onto. This is where the second main component of the grammar of graphics comes into play. On top of layering the grammatical elements, it's here that we establish our aesthetic mappings. In this case, we are going to make a scatter plot, so we're going to map sepal.length onto the x-aesthetic and sepal.width onto the y-aesthetic. The next element is the geometry element. This allows us to choose how the plot will look. After we've established our 3 essential layers, we have enough instructions to make a basic scatter plot. It's pretty rough, so to get a more meaningful and cleaner visualization, we'll have to use the other layers. The next layer we'll look at is the themes element. It controls all the non-data ink on our plot, which allows us to get a nice-looking, meaningful, and publication-quality plot directly in R. We'll discuss the remaining grammatical elements in the next course. For now, let's begin by exploring these concepts in the exercises. In this section, we'll explore aesthetics and understand how they're distinct from attributes. In ggplot2, the mapping of aesthetic elements is a key concept to master. So, what do we mean by mapping? This becomes clear when we understand that our beloved x and y axes on a straightforward scatter plot are aesthetics. They define the position of dots on a common scale, like this example we saw in the previous chapter. The sepal length is mapped onto the x aesthetic, and the sepal width is mapped onto the y aesthetic. Here, we'll focus on the most common visual aesthetics, but we'll encounter more throughout the courses. When making multivariate plots, we'll use aesthetics appropriately to maximize the number of variables we can add to a plot. For example, the variable species can be mapped onto the color aesthetic, which colors the points according to the species from which they came. That is, we map a variable from our data frame onto one of the visible aesthetics. We call a column in our data frame to be mapped onto a visible aesthetic. That's why we made such a big deal about data structure earlier. Each mapped variable is its own column variable in the data frame. Importantly, we call aesthetics in the AES function. We could have also called aesthetics in the geom layer, as shown here, and get the same result. This is typically only done if we don't want all layers to inherit the same aesthetics, or we're mixing different data sources. In general, try to keep your data and aesthetics layers in the same ggplot function definition. In addition to the x and y axes and color, typical visible aesthetics include fill, which is distinct from color in that color usually, but not always, refers to the outline of a shape. Size adjusts the area or radius of points, the thickness of lines, and the font size of text. Alpha refers to alpha blending, which adjusts the transparency of a shape. Line type refers to the dash pattern of a line. And labels are direct labels of an item directly on a plot, like printing an item's name on a scatter plot instead of just drawing a point. Direct labeling of points is an extension of access labels for categorical data in that they are unambiguous. And shape refers to the shape of a point. Many of these aesthetics function as both aesthetic mappings as well as attributes, and one of the most common mistakes beginners make is to confuse the two or overwriting aesthetic mappings with fixed attributes. Our goal here is to not only show you how to use them correctly, but appropriately for the plot's type and purpose. Just like our two main variable types, there are visible aesthetics for continuous and categorical data, which we'll explore in a later video. For now, let's head over to the exercises and take a look at how aesthetics work. In the last exercises, you learned a fundamental concept of ggplot2, aesthetic mappings. Colloquially, when we say aesthetics, we're describing how something looks, but now you know that in ggplot2, we're talking about aesthetic mappings. If we talk about how something looks, we refer to its attributes. One of the most confusing parts of ggplot2 is that all of our visible aesthetics also exist as attributes. So it's easy to mix up the two. Attributes are always called in the geom layer, which we'll discuss in more detail in the next chapter. For example, to change the color of these points to red, we just set the plot's attribute using the color argument in the geom layer. For example, its color attribute is set by the color argument, its size by the size argument, and its shape by the shape argument. The distinction between aesthetics and attributes is subtle but important. Mixing the two is a very common mistake. Okay, let's wrap up with some exercises on setting attributes. Now that we know what aesthetics are and have some idea about choosing them appropriately, let's explore how to modify them. A common adjustment is the position. Position specifies how ggplot will adjust for overlapping bars or points on a single layer. For example, we have identity, dodge, stack, fill, jitter, jitter dodge, and nudge. Let's take a look. The most straightforward position is identity, which we've actually already seen. It's the default position for our scatter plots. Identity means that the value in the data frame is exactly where the value will be positioned in the plot. This basically means don't do anything. Just put the information where the data says to put the information. We could have written it explicitly, but it's not necessary. There is an issue with the precision in this data set. Our sepals were measured to the nearest millimeter. So although we only have 150 points, there is too much overplotting to distinguish them. To solve this, we need to add some random noise on both the X and Y axes to see regions of high density, which is referred to as jittering. Jitter can be used as an argument, but each position type can also be accessed as a function. For example, position jitter can be defined in a function before we call our plot, as shown here. This has two advantages. Now we can set specific arguments for the position, such as the width, which defines how much random noise should be added, and it allows us to use this parameter throughout our plotting functions so that we can maintain consistency across plots. This is available for all position attributes. We'll explore the other positions in the exercises. Recall that each of the aesthetics is a scale which we mapped data onto. So color is just a scale, like X and Y are scales. Appropriately enough, we can access all the scales with the scale underscore functions. The second part of the function defines which scale we want to modify. All the aesthetics we saw earlier have an associated scale function. The third part must match the type of data we are using. Here, discrete means we are working with categorical data. That means we have to choose our axis dependent on the type of data we have. Here, we'll consider the continuous X aesthetic and the categorical color aesthetic. Just as an aside, before we move on, don't let the naming conventions confuse you. Categorical variables are also called factors, discrete, and qualitative, depending on their context and who you're talking to. There are many arguments for the scale functions. The first argument is always the name of the scale. After that, most common are limits, breaks, expand, and labels. Limits describe the scale's range. Breaks control the tick mark positions. Expand is a numeric vector of length 2, giving a multiplicative and additive constant used to expand the range of the scales so that there is a small gap between the data and the axes. And labels adjust the category names. Note that if we just want to quickly change the axis labels, we can do this with the labs function. Alright, now let's try it out in the exercises. Now that we know what visual aesthetics are, how do we choose the right one? There is some creativity involved, but there are some helpful guidelines. This chapter is informed by the seminal work of cartographer Jacques Bertin, who published a Semiology of Graphics in 1967, and William Cleveland, whose research on perception was summarized in 2 books. The best data viz serves a purpose. That is, form follows function. So, what is the function in data viz? Well, it depends on your audience. You may just want to confirm expectations and begin analyzing your data, or you may want to inform a specific reader and persuade them with your results. First and foremost, our function is the accurate and efficient representation of data. Beautiful is nice, but it's a secondary priority here. If data is not accurately and efficiently presented, it's junk. The function is never to misrepresent or obscure our data. We can avoid this by always considering the intended audience and purpose of our plots. So how do we do this? Let's look at a simple example. In this dataset, I have two continuous variables, x and y. Y is a function of x. There are two groups, A and B. It's pretty difficult to obtain summary statistics just by looking at the data. So we have two choices, numeric summaries, which are precise but offer a poor overview, or data visualization, which is imprecise but is great for overviews. To make a plot, we encode data in numbers and text into a visual medium. That's what we do with aesthetic mappings. These plots differ in their aesthetic mappings and other values that we'll explore throughout the courses. These visuals are then decoded to form an image of the original data. It's inherently imprecise, kind of like translating between two languages. We consider the best choices to be those which are both efficient in that they are faster than numeric summaries and accurate in that they minimize this information loss. The choice of aesthetic mapping depends on the type of variable. The scatter plot is so easy to understand because it maps data as position onto a common scale. Imagine if we switch the aesthetic mappings for X and color. This is possible, but is neither accurate nor efficient. In the worst case scenario, there is no way to see the relationship between these three variables. And in the best case, our reader will interpret the plot in an unintended way. There are many choices for mapping continuous variables. For example, position on unaligned scales, as in having many plots with different scales but the same data type, like this example where we had three plots from the iris Y2 data frame, one for each of our iris species, on unaligned y-axes, is less efficient and makes it difficult to compare plots compared to unaligned scale. There are also a variety of choices for categorical data. Color is often used to good effect for a categorical variable. But efficiency and accuracy are not only functions of aesthetic mappings. This plot suffers from overplotting since not every point is visible. Overplotting is an issue whenever we have points, like in a scatter plot. We'll see lots of examples of overplotting and how to deal with it in the exercises. Here, we'll want to adjust position to add some random noise and attributes, which we've already seen. Let's head over to the exercises and play around with these concepts further. The third essential layer is the geometry layer. This determines how the plot actually looks. We've already seen many geometries in action, so let's take a closer look. At present, there are almost 50 different geometries to choose from, although there are some redundancies. Geometries can be accessed using their own geom function. As a domain specialist, it's your job to choose the best geom, but there are some useful guidelines. Let's begin with scatter plots. Each geom is associated with specific aesthetic mappings, some of which are essential. To use geom point, we need the X and Y aesthetics. In addition to the essential aesthetics, we can also choose optional aesthetics, like alpha, color, fill, shape, size, or stroke. These are all attribute settings, as we discussed earlier. We can specify both geom-specific data and aesthetics. This allows us to control the information for each layer independently. Imagine I have a data frame which contains summary statistics, such as the mean for each of my variables. In this case, it's the average sepal length and width for each of the three iris species. ggplot2 can actually take care of the statistics for us, We don't need to calculate it ourselves beforehand, but let's see how to use it if we have. To show all the individual points and have the mean of the x and y plotted on top, I could add another geom point layer accessing this dataset. In this plot, one geom point layer inherits the data and aesthetics from the parent ggplot function, and in the other, I specify a different dataset. Note that the aesthetics are inherited as per the first geom function. I've changed the shape and the size attributes of the points so that they are distinguishable from the background points. The possible values are shown here. 15 is a solid square. Numbers 21 to 25 are not simply repeats of earlier codes. These shapes have both fill and color, which can be controlled independently. For example, I can have a black fill and use a stroke of 2 for a thick outline. The color aesthetic is still inherited from the parental layer. Imagine I wanted to have crosshairs marking where each mean value appears in the plot. It's not fair to plot the mean without some measure of spread, like the standard deviation. We'll get to that in the next course when we discuss the stats layer. Recall that in the last chapter, we used a position argument to change the position from identity to jitter. We could have also done this with a geom jitter function directly. Geom jitter is just a wrapper for geom points with position set to jitter. On top of jittering, we would also need to deal with overplotting points by adjusting the alpha blending, which works great as an attribute. This helps us to see regions of high density. Yet another way to deal with overplotting is to change the symbol to a hollow circle, which is shape 1. Both of these options help with visual communication because they aid in perception. We can more accurately and quickly see what the data is actually showing, even if the jittering adds some random noise to both axes. It's always recommended to optimize the shape, size, and alpha blending of points in a scatter plot. Let's head over to the exercises to understand what overplotting is and how to deal with it. In this section, we'll take a look at the typical uses of bar plots and their associated geoms. A histogram is a special type of bar plot that shows the bin distribution of a continuous variable. Here, we only need a single aesthetic, x, a continuous variable. Geom histogram plots a bin version of our data. A message lets you know what happened. This geom is associated with a specific statistic, stat bin. The bin argument took the default value of 30 bins. This is a good starting point, but we don't need to settle for defaults. Let's change it and see what happens. Changing the bin width argument to 0.1 gives us a more intuitive impression of our data. Note that there is no space between the bars. That emphasizes that this is a representation of an underlying continuous distribution. That's also why the labels on the x-axis shouldn't fall directly on the bars, but between the bars. They represent intervals and not actual values. Setting the center argument to half that of the bin width does the trick. Remember that we have 3 species in our dataset? We can fill the bars according to each species. This makes it clear that we have 3 histograms in the same plotting space. There is a perceptual problem here because it is not immediately clear if the bars are overlapping or if they are stacked on top of each other. The default position is stack. In some cases, this may not be clear, so don't risk confusing your viewer with stacked bars. We have some alternative positions we can use. We can dodge our bars, which is a database term that simply means to offset each data point in a given category. That works, but the number of categories really makes it difficult to see what's happening. We'll encounter dodging again in several situations throughout these courses where it can be used to good effect. The fill position normalizes each bin to represent the proportion of all observations in each bin. The y-axis label didn't change, but it should say proportion, not count. All right, let's head over to the exercises and take a look at histograms in action. In the last video, we saw that histograms are a specialized version of bar plots, where we have binned a continuous x-axis. Classic bar plots refer to a categorical x-axis. Here, we need to use either geom_bar or geom_col. Geom_bar will count the number of cases in each category of the variable mapped to the x-axis, whereas geom_col will just plot the actual value it finds in the dataset. All the positions we just looked at are available in bar plots. You will encounter two types of bar plots in widespread use, depicting either absolute counts or distributions. Let's take a look at them in turn. We'll use a dataset containing information on the REM sleep time and eating habits of a variety of mammals. In this bar plot, we split our dataset according to eating behavior and simply asked how many observations we have in each category. Notice that something very similar to what happened with geohistogram has happened here. The data was counted and that count was plotted. So once again, there were some statistics which occurred under the hood. In this case, there was a default value of bin set for the stat argument. These kinds of plots are useful in getting a quick visual output, but we often see another type of bar plot, one which tries to depict the distribution of a dataset. Let's consider a scenario similar to what we saw with the geom point, that we have a dataset with the summary values already calculated. Oftentimes, this is the case. You will have descriptive statistics already calculated, but remember that we can make ggplot do this on the fly. If we want to plot the average sepal width for each species, we can map the AVG column in our dataset to the Y aesthetic. In this case, we need to use geom_col. If we want to add error bars, there is another geom for that, appropriately called geom_error_bar. Here, we need to specify some aesthetics specific to this geom, namely ymin and ymax. On top of that, I've set the width of the error bar tips to be narrow, and I've made the fill of the bars themselves gray so that we can see the error bars. This is the kind of plot that you'll typically see in scientific publications, but it's pretty terrible. There is a special name in the Data Viz community for these types of plots. They're called dynamite plots, as in Wile E. Coyote and the Roadrunner and a giant stick of Acme dynamite. They are strongly discouraged for many reasons, which we'll explore in the Data Viz Best Practices chapter at the end of the second course. Let's head over to the exercises and take a look at bar plots in action. Line plots are another very common plot type. We'll take a look at two examples of line plots in situations in which they are very well suited, time series. In this first example, our dataset contains temperature measurements of a beaver in 10-minute intervals over 16.5 hours. The time variable is in a proper time format, which can be handled very well with ggplot2. Our basic line plot follows the syntax we've seen so far. This is the simplest case scenario. Let's look at adding additional variables. In this case, the transponder in our beaver also measured if the beaver was active or not. We can directly color each segment of our line according to another variable, which is set as a color aesthetic. In the fish dataset, we have the global catch of 7 varieties of salmon over a 60-year period. When we have multiple lines, we have to consider which aesthetic is more appropriate in allowing us to distinguish individual trends. Using line type makes it difficult to distinguish individual species. Using size is even worse. Don't forget to use your common sense here. Using color allows for easily distinguishable groups. There are a couple other ways of showing lines. The most salient choice is color, when available, since it allows the easiest way of distinguishing between each series. For example, we could have used an area fill with geom area, which defaults to position stack. So instead of overlapping time series, they are added together at each point. This kind of works in this situation. It really depends on how many time series you have and if that is what you want to communicate. If we use position fill, we'll get a proportion of the total capture for each fish at each time point. Note that we need to change the y-axis label since these are no longer counts. This kind of plot is pretty popular in looking at proportional trends over time. A difficulty with this kind of plot is that only the bottom and top groups are actually drawn on a common scale. All the other ones are irregular shapes, so they can be a bit difficult to decipher. The final type of plot we'll look at is when we would want to have overlapping areas. In this case, we'll have to use geom ribbon and force the y-min to be 0. We need to set the alpha level so that we can see the overlap. There is still a challenge in deciphering all the time series, in particularly at the bottom, where there are many overlapping series. We'll explore line plots in the following exercises, which will bring our discussion of the first 3 essential layers of ggplot2 to a close. By now you have a good core knowledge to build a wide variety of plots. I'll see you in the next chapter, where we'll talk about making clean explanatory plots by using the themes layer. The themes layer controls all the non-data ink on your plot, which are all the visual elements that are not actually part of the data. Visual elements can be classified as one of three different types: text, line, or rectangle. Each type can be modified by using the appropriate function, which all begin with element underscore followed by text, line, or rect, respectively. For example, consider this plot that we've already encountered a few times. It's composed out of a combination of data and lots of non-data embellishments. For example, these are all the text elements on our plot. Each element has its own unique name. We can access all the text in general, all titles in general, but also more and more specific items, such as the plot, legend, and axis titles, or the text on specific axes. All these items are arguments in the theme function. This is used like all other layers in ggplot2 by adding a plus to our plot. To modify an element, just call its argument in the theme function and use the appropriate element function to specify what we want to change. In this case, we need to use an element text call. It's within this function that we manipulate things like size, color, alignment, and angle of the text. Lines include the tick marks on the axes, the axis lines themselves, and all grid lines, both major and minor. These are also all just arguments within the theme function and are modified by the theme line argument. The remaining non-data ink on our plot are all rectangles of various sizes. Access rectangles using arguments in the theme function and modify them using element rect. Although we have access to every item, we don't need to modify them individually. They inherit from each other in a hierarchy. All text elements inherit from text, so if we change that argument, all downstream arguments would be affected. The same goes for line and rectangle. The naming convention is pretty intuitive. In practice, you will call a small combination of arguments that you want to change. There is one other element function that we haven't discussed yet: element blank. We can use this in a plot to remove any item, that is, it won't be drawn at all. In this example, we set all lines, text, and rectangles to blank, so we are left with just the data. Notice that the legend keys themselves are part of the data. If you want to modify these elements, refer back to the chapter aesthetics and the exercises on scales. Here, we saw how the theme layer allows us to modify visual attributes of non-data ink, including text, lines, and rectangles. But in addition to that, we can also modify a plot's margins and legend position. Let's head over to the exercises and see this in action. In the last video and exercises, we saw how to fine-tune every part of our plot using the theme layer. There are a few other ways of changing theme elements, so let's take a look. We'll begin with defining our own theme layer object. If you're using many plots within a presentation or publication, you'll want to have consistency in your style. So once you settle on a specific theme, you'll want to apply it to all plots of the same type. Creating a theme from scratch is a detailed process that we don't want to repeat for every plot we make. That's where defining a theme layer object comes into play. To see how this works, let's return to a plot we've already seen in the last video. For convenience, we're going to save this plot as an object called Z. We can adjust specific theme arguments to get the desired plot style. Here, I've changed the font family, size, and title color. The first method in automating this process is to save our layer as an object. Here, we're just going to call it Theme Iris. Just as we've seen throughout the course, we can add individual layers to any ggplot object. This means that we can reuse the style over and over. Let's see what happens when we try to apply our new theme object on another plot. Remember this histogram of the iris sepal widths? Now it has the same style as our scatter plot, without having to retype the whole theme layer. But let's say that on occasion, I want to modify some other specific elements of a plot. Not a problem. We can just add another theme layer which will override any previous settings. In this example, I've removed the x-axis line. So far, we just used our theme as an object itself. This is a pretty flexible way of working with a theme. But a third way of working with themes is accessing the built-in themes template. Built-in theme functions begin with theme underscore. Theme classic is my go-to template for great publication quality plots. Of course, we can always modify any specific element, as we've already seen. There are also packages with predefined themes, like the ggthemes package. The Tufty theme mimics Tufty's classic style, which removes all non-data ink and sets the font to a serif typeface. Finally, we can update and set the default theme. Updating is done with the theme update function. This function behaves differently from a typical function. This command updates the default theme and saves the current default to the object original. Now, all plots will automatically have the same theme. We can set a complete theme object, like original, using the theme set function. By now, you have the ggplot2 core competencies that will allow you to make beautiful and effective exploratory plots. But there is still a lot more to data visualization and ggplot2. Alright, let's take a look at these concepts and themes in the exercises. For our last exercises, I want to go through an example of producing explanatory plots in an InfoVis style, something that you see in a magazine or website for a mostly lay audience. These plots tend to have both a small number of observations and variables, have embellishments, and typically make a clear or dramatic statement message. Our example comes from the Gapminder dataset and plots the countries with the highest and lowest life expectancies in 2007. The global mean is plotted for comparison. Here, we focus on the large gap between the highest and lowest life expectancies, which is about 40 years. We would begin with our complete dataset, which contains 3 variables for 142 countries. Our first exploratory plot would probably be a histogram, which isn't a bad choice. Recall that we have already applied a binning statistic here. An alternative would be to arrange the data according to life expectancy and plot that as an index, which allows us to see each point individually without first binning the variable. This has the advantage that we can color each point according to the continent. This is already a quite informative plot. We can see differences in the distribution between continents. After getting familiar with our data, we need to reduce it to a compact and understandable component for a lay audience. In this form, we only have 20 observations, the top 10 and bottom 10 observations. Here, I'd map the country to the y-axis so that it's easy to read. I map life expectancy onto both color and the x-axis, which is redundant but helps a lay audience. The line segments add some perspective and is sometimes referred to as a lollipop plot when used with points. Typically, we're happy to just read a value from the axis, but adding the actual value using a geom text layer makes it immediately more intuitive for unexperienced viewers. You can already see that there are many things happening that we wouldn't typically do for a scientific audience. Next, I clean up the scales, using an intuitive color palette, removing unnecessary buffering, and changing the x-axis location to the top of the plot. Titles and captions help to make the plot complete, if it will be viewed alone. And of course, removing non-data ink makes for a great-looking plot. Notice that I removed the x and y-axis labels as well as the legend. None of them are actually necessary. Adding a threshold line helps to orientate the viewer. Here is the global mean from 2007. Of course, it's also helpful to label the threshold line. We'll do this with the annotate function, which allows us to access any geom and place it manually on a plot. For example, another geom we haven't seen yet is geom curve, for drawing curved lines. This is really great for adding handy little arrows anywhere on our plot. By now, you have the ggplot2 core competencies that will allow you to make beautiful and effective explanatory plots, but there is a lot more to data visualization and ggplot2. After you finish the exercises, head over to the next course and learn about the remaining layers to round out your knowledge.